Somewhere in the deep record of the Earth, locked inside layers of ancient ice and settled mud and the slow-grown rings of cave stone, there is a moment. Not a gradual drift, not a gentle cooling over centuries, but something closer to a door swinging shut. A shift so abrupt that when scientists first encountered the evidence, some of them assumed they'd made a mistake. The numbers simply didn't seem possible. Temperatures across large parts of the northern hemisphere dropping by several degrees within what appears in geological terms to be almost no time at all. Not over millions of years, not over thousands. Something far more unsettling than that. This is a story about that moment. About 12,700 years ago, give or take the uncertainty that always comes with reaching that far back, something happened to the climate of this planet. The world had been warming, slowly, hopefully, edging out of an ice age, and then it stopped. More than stopped, it reversed. A cold interval descended that would last for roughly 1,200 years, and the world that emerged on the other side of it was different from the one that went in. What caused it is still, genuinely, a matter of serious scientific debate. There are competing theories, passionate disagreements, evidence that seems to point in several directions at once. Some researchers have spent careers building a case for one explanation, only to watch new data complicate everything they thought they knew. That's not a failure of science. That's science working exactly as it should, honest about what it doesn't yet understand. So tonight, we're not going to arrive at a single definitive answer, because there isn't one. What we're going to do instead is follow the evidence, explore the ideas, and sit with the mystery the way researchers themselves have to sit with it. Carefully, curiously, and without pretending the question is simpler than it is. Before we go any further, I want to ask you something. If you're watching this right now, if the screen is dimmed and you're settling in, where are you? What time is it there? Are you in a city where the lights outside your window never quite go dark, or somewhere quiet where you can actually hear the night? I always read the comments on these videos, and it genuinely fascinates me that someone might be listening to this from a morning kitchen in Melbourne, while someone else is drifting off at midnight in Edinburgh, and someone else is watching from a highway rest stop in Oklahoma at 2 a.m. All of us, together, thinking about the same ancient cold. Leave a comment and let me know. It matters more than you might think. Now, back to the cold. The event we're going to explore goes by a name that sounds almost poetic for something so severe. Scientists call it the Younger Dryas, named after a small flowering plant, a white-petaled tundra flower whose pollen began appearing in European sediments as temperatures fell and the landscape shifted back toward something glacial. The flower thrived in the cold. Its presence in the mud layers became a marker, a signal that could be read thousands of years later by people patient enough to look. And there are so many signals once you know where to look. Ice cores drilled from Greenland, sediment pulled from the floors of ancient lakes, stalagmites that grew one slow drip at a time inside dark caves. Each of these carries a record, imperfect and partial, but real. Each of them is a kind of message from a world that experienced something extraordinary and left traces behind for us to find. We're going to follow those traces tonight, gently, without rushing. The story is long and the night is quiet, and there is no better time to think about an ancient cold than right now. To understand what was lost when the cold came, you have to understand what was being built. In the centuries leading up to 12,700 years ago, the world was in the middle of something remarkable. The great ice sheets that had pressed down over North America and Northern Europe for tens of thousands of years were retreating. Slowly, unevenly, with setbacks and surges, but retreating. The glaciers that had once buried what is now Chicago under a mile of ice were pulling back toward the north. The tundra that had stretched across much of Europe was greening at its edges. Summer temperatures were climbing. The planet was, in a very real sense, waking up. This warming period had a name, the Bulling-Alarud Interstadial, and if you'd been alive during its peak, the world around you might have felt genuinely hopeful. In Western Europe, forests were beginning to spread into areas that had previously been open grassland, birch and willow moving north, following the warmth. In North America, the vast prairies east of the retreating glaciers were home to horses, camels, mammoths, and giant ground sloths, animals whose diversity rivaled anything alive on the African savanna today. The North Atlantic, which drives so much of the Northern Hemisphere's climate, was circulating in ways that pumped warmth northward, keeping temperatures elevated across a remarkable stretch of the globe. This wasn't paradise, exactly. The Ice Age hadn't ended. There were still enormous ice sheets in the high north. Sea levels were lower than today. The climate was variable in ways that could be brutal. But the direction of travel was clear. Things were getting warmer. The great glacial cold was releasing its grip. And then something interrupted that process in a way that still doesn't have a fully satisfying explanation. When scientists talk about an abrupt climate shift, they mean something specific, and it's worth slowing down to appreciate what that actually means in practical terms. The climate system of this planet is enormously complex. It involves ocean currents that move heat across thousands of miles, atmospheric patterns that determine where rain falls and where it doesn't, ice sheets that reflect sunlight back into space and influence temperatures far beyond their own edges. Under normal circumstances, these systems change gradually, over centuries and millennia, adjusting to slow shifts in the Earth's orbit or the gradual rise and fall of greenhouse gases. A degree of warming or cooling over 1,000 years is, in geological terms, fairly brisk. Over a century it's remarkable. Over a decade it's startling. Over the span of a single human lifetime it would be almost incomprehensible. What the Younger Dryas appears to have done was something in that last category. The affected regions stretch across an enormous swathe of the northern hemisphere. The North Atlantic cooled sharply, with consequences that rippled outward in every direction. Europe, which had been edging towards something almost temperate, shifted back toward tundra conditions across much of its northern half. North America, still shedding its glaciers, experienced a halt, and in some areas a reversal. Evidence suggests disruptions reached into the Middle East, where early human communities were just beginning to experiment with settled life and deliberate cultivation of wild grains. Whatever happened was not a local anomaly. It was systemic. And this is the question that sits at the heart of everything we'll explore tonight. What could interrupt a warming world so completely, so quickly, across such a vast geographic range? What kind of force operates on a scale large enough to reach from the ice sheets of Greenland to the river valleys of ancient Syria? And why did it happen precisely then, in that window, during what seemed like an irreversible thaw? The answer, as you might have guessed, is still being argued over. But the arguments themselves are fascinating, and they begin, as so many climate stories do, with the ocean. Before we can follow the arguments about what caused the Younger Dryas, we have to sit with a simpler, and perhaps more quietly astonishing question. How do we know any of this happened at all? The events we're discussing unfolded 12,000 years before anyone wrote anything down. No scribes were present, no astronomical records survive. The people who lived through it left no account we can read. And yet scientists speak about the timing and temperature of these changes with a specificity that can feel almost unsettling. A shift of several degrees in perhaps a decade. A transition beginning within a human lifetime. How does anyone actually know that? The most important answer begins in Greenland, in the form of ice. Snow falls on the Greenland ice sheet every year, and every year that snow compresses under the weight of what falls above it, eventually becoming ice. What makes this process extraordinary, from the perspective of someone trying to understand ancient climate, is what gets trapped inside as the compression happens. Air, actual air from the year the snow fell, sealed into tiny bubbles within the ice crystals. When scientists drill down through the ice sheet and extract a core, they are pulling up a physical archive that is layered like the pages of a book. Each layer represents a year. Each bubble contains a sample of the atmosphere from that year. At the surface, you're reading the recent past. 100 meters down, the medieval period. 1,000 meters down, you're breathing, in a sense, the air of the deep ice age. The layers themselves carry information. The thickness of each annual band tells you something about snowfall. The chemistry of the ice tells you about temperature. This is where a particular kind of measurement becomes essential. Water molecules are not all identical. Oxygen comes in different isotopic forms, and the ratio between two of them, oxygen 16 and oxygen 18, changes in a predictable way depending on how cold or warm the atmosphere was when the snow formed. Colder temperatures produce ice with relatively less oxygen 18. Warmer temperatures leave more of it behind. By measuring this ratio at different depths in the core, scientists can construct a temperature record that extends back hundreds of thousands of years. What those ratios show, in the Younger Dryas layers, is a shift dramatic enough to be visible almost immediately when you look at the data. The oxygen isotope signature drops sharply, indicating a significant cooling. Then, roughly 1200 years later, it rises again, equally abruptly. The transitions are so distinct that they were among the first pieces of evidence that the climate system could change not just gradually, but in jumps, in lurches, in a matter of years rather than centuries. But ice cores are only one voice in a much larger conversation. Lake sediments offer a completely different kind of record. When organic material settles to the bottom of a lake, it builds up over time in layers that can be sampled and analysed. The pollen preserved in those sediments tells you what plants were growing in the surrounding landscape. Forests produce different pollen than open grasslands. Cold-tolerant species produce different pollen than warmth-loving ones. In European lake sediments from the Younger Dryas period, you can watch the ecological shift happen in real time, the pollen of warmth-adapted trees retreating, replaced by the signature of cold scrubland and tundra vegetation. Then, at the end of the interval, the forest returns. Ocean sediment cores add yet another layer. The tiny shells of microscopic organisms called foraminifera accumulate on the ocean floor over millennia. Different species of foraminifera prefer different water temperatures, and their isotopic chemistry carries temperature signals similar to those in ice. By counting species and measuring isotope ratios at different depths in a sediment core, oceanographers can reconstruct how cold the surface waters were in a given region and when. The North Atlantic records show the same cooling interval, approaching it from a completely different archive, using completely different organisms, using different chemistry. Cave formations called speleothems, the stalactites and stalagmites that grow slowly from dripping mineral-rich water, offer something else again. The chemistry of each growth layer reflects the temperature and precipitation patterns of the time it formed. Growth rates can slow or stop during cold dry periods and accelerate during warmer wetter ones. Caves across Europe and the Middle East carry records of the Younger Dryas in their stone, silent and patient and extraordinarily detailed. What's remarkable is not that any one of these archives exists, it's that they converge. Ice cores from Greenland and lake sediments from Germany and ocean cores from the North Atlantic and cave deposits from Turkey are all telling the same basic story, even though they were formed by entirely different processes, recorded by entirely different materials, and analysed by research teams who sometimes worked independently of one another for decades. That said, they don't agree perfectly, and this is worth sitting with honestly rather than brushing past. Dating these archives involves its own uncertainties. Ice core chronologies rely on counting annual layers, which becomes more difficult and imprecise in older, more compressed ice. Radiocarbon dating of organic material in lake and ocean sediments carries margins of error that can span decades or even a century or two. Different archives place the start of the Younger Dryas at slightly different moments, and the end of it at slightly different ones. When scientists give a date of roughly 12,700 years ago for the onset, they are speaking in ranges and probabilities, not the kind of precision a stopwatch could provide. But here is what those margins of error don't undermine: the fact that something happened, something large and real and hemispheric in its reach. The convergence of independent evidence from ice and stone and sediment and shell, all pointing to the same general window, the same direction of change, the same approximate duration, is the kind of agreement that doesn't emerge from coincidence. Each archive has its own imprecision. Together they build a case that is, in its broad outlines, as solid as almost anything we know about the deep past. And that solid foundation is what makes the question of cause so maddening. We know the event happened. We know roughly when and roughly how fast and roughly how severe. What we still can't fully agree on is why. If you were standing on the ice sheet in Greenland when that isotope line in the core suddenly bent downward, you probably wouldn't have noticed anything dramatic on that particular day. No sudden roar, no instant wall of frost racing across the horizon. Climate rarely announces itself in a single moment. But over a span of seasons, of a few years, the world around you would begin to feel off. The key thing to understand is that this cooling was not a neat, even blanket draped over the planet. It was a patchwork. Some regions plunged into deep cold, others cooled only slightly. A few may even have stayed relatively mild, at least compared with the new conditions in the far north. Imagine the North Atlantic world first, because that's where the signal is strongest. In what's now northern Europe, forests that had been creeping back after the last glacial maximum suddenly stall. In some places they reverse. Pollen in lake mud tells the story in astonishing detail. One layer is rich in the signatures of birch and pine, of warmth-tolerant shrubs trying to reclaim the land. A few centimetres higher in the core, those pollens thin out, replaced by the grains of hardy grasses, sagebrush-like plants, and dwarf shrubs that can tolerate wind-scoured, nutrient-poor soil. On the ground, that translation is simple. Stands of trees that had been thickening along river valleys begin to look patchy. Saplings die back in late frosts. Young leaves are browned by cold snaps that arrive when they shouldn't. Open ground, once slowly filling in with woodland, becomes a mosaic of scrub and bare soil again. Further north, in areas already marginal, the change is harsher. What had been a tundra speckled with scattered dwarf trees and shrubs shifts towards something closer to steppe. Low, tough plants hug the ground. The growing season, already brief, shrinks by weeks. Snow lingers longer in the shadows. The first green appears later. The last killing frost arrives earlier. A year is still a year, but the part of it where plants can actually grow is smaller. If you were a reindeer, a muskox, or a horse picking your way across that landscape, this matters more than a graph of average temperatures ever could. It's not that the whole year is suddenly unbearable. It's that the crucial windows for fattening up, for raising young, for growing antlers and storing energy, become tighter. Far to the south, meanwhile, the story is different. In parts of the Mediterranean, for example, the pollen record suggests cooler and drier conditions, but not an abrupt plunge into deep freeze. Forests thin but don't vanish. Rivers shift their patterns, some lake levels drop. Winter storms may become more frequent or intense, but overall the Younger Dryas here looks more like a stubborn interruption of warming than a full return to Ice Age severity. Across much of the tropics, evidence points to changes in rainfall rather than temperature alone. Some monsoon systems weaken. Certain regions become drier, others wetter. For the people living there, the Younger Dryas may have been felt less as cold and more as unreliable rains, failed growing seasons, or new patterns of flood and drought. This is what it means to say the climate system reorganized. Not that one global thermostat was turned down by a fixed amount everywhere, but that wind belts, storm tracks, ocean currents, and seasonal cycles all shifted relative to one another, rearranging where heat and moisture flowed. Even within a single region, the experience would have depended on where you stood. Consider the margins where forests met open ground, where tundra graded into steppe, where permanent ice gave way to summer melt. These edges, called ecological boundaries, are some of the most sensitive parts of the landscape. During the Younger Dryas, many of them moved, southward, mostly in the northern hemisphere. Imagine a valley that for a few generations has been a rich hunting ground for large herbivores. Mammoths or woolly rhinoceros in some places, giant deer or wild horses in others. Their presence depends on a particular combination of grasses, shrubs, and seasonal water. As the climate cools and drying patterns shift, the plants they rely on thin out or change composition. The valley doesn't become barren overnight, but it becomes less ideal. Calves don't survive as well. Herds get smaller. Eventually, the animals follow the line of their preferred habitat as it retreats, perhaps dozens or hundreds of kilometers away. To the people who depend on them, this looks like a gradual abandoning of old routes. Tracks are harder to find. Old migration paths fail. The timing of animal movements becomes less predictable. It's not that the beasts go extinct in your mind. They just stop coming where they used to. Elsewhere, other animals may find new opportunities. Cold-tolerant species expand into areas that had been too warm and wooded before. Predators follow their prey. The cast of characters on the landscape changes, even if the number of degrees on the thermometer is not something anyone can name. Winters likely grew sharper in many parts of the North Atlantic region. Not just colder nights, but more days below freezing, more frequent snow cover, more episodes of freezing and thawing that could create ice crusts on top of snow, locking away the grasses below. For grazers, that kind of crust can be deadly. For hunters, it changes where and how animals move, and sometimes makes tracking easier, right up until the herds collapse. Storms may have shifted too. With an altered temperature gradient between equator and poles, the tracks of Atlantic storms could have been displaced. Winds might have blown from slightly different directions, bringing snow to places that had rarely seen it, or leaving other regions worryingly dry. If you were tending wild stands of grain on a Near Eastern hillside, harvesting, burning, lightly disturbing the soil to encourage better yields, you might notice that some years late frosts blacken the ripening heads. Other years, dry spells stretch just long enough that the seeds don't fill properly. The crop still appears, but the margin between abundance and hunger narrows. What had looked like a reliable pattern turns fickle. In many ways, the Younger Dryas on the ground would feel less like the temperature dropped by X degrees, and more like this. The familiar rules of the seasons stopped holding as well as they had. The plants you expected in certain places retreated. The animals that followed certain routes broke their habits. Snow lingered where it used to melt. Rains shifted to different months or skipped entire years. For the people living through it, there was no global name for this interval, no sense of being inside a precisely dated climatic event. There was only the lived reality of a world subtly but persistently rearranging itself, forcing constant readjustment. A forest that would not return where elders said it once stood. A steppe marching south. Summers that came late and left early. From our distance we can measure isotopes and count pollen grains. We can draw curves on graphs and label them with tidy dates. But for those on the ground, the Younger Dryas was not a line in an ice core. It was the slow revelation that the rules of their landscapes were changing, and that the old map in the mind of where to find food, when to expect snow, which valleys belonged to which animals, would have to be redrawn. To understand why so much of this rearrangement was focused around the North Atlantic, you have to zoom out from hillsides and river valleys and look at the ocean itself, not as a flat blue surface on a map, but as a moving, breathing thing. The Atlantic especially is not just a basin of water, it's part of a global engine that moves heat around the planet. Today, people sometimes call it the Atlantic Meridional Overturning Circulation. You can think of it more simply as a vast conveyor belt, made of water instead of rubber, powered not by electricity but by differences in temperature and salt. Here is the basic idea. Warm, salty water flows northward near the surface of the Atlantic. As it travels, it releases heat to the air above it. That warmth is carried by winds over to Western Europe, which is one reason why some places at the latitude of Labrador can grow vineyards instead of permafrost. As the surface water in the far North Atlantic gives up heat and mixes with colder air, it cools. As it cools, something important happens. Its density increases. The high salt content helps with this too. Cold, salty water is heavier than warm, fresher water. At a certain point, in certain key regions near Greenland and the Nordic seas, that surface water becomes dense enough that it sinks. It plunges down into the depths and begins slowly flowing southward again, thousands of meters below the surface. Heat goes north near the top, cold returns southward below. In between, there are all kinds of swirls and eddies and side branches, but that broad pattern, northward warmth, sinking, southward cold, is one of the main reasons the North Atlantic region is as mild as it is between ice ages. Now imagine that conveyor as something surprisingly fragile, because for the sinking step to work, the water up there has to be salty and cold enough to become very dense. Change those conditions even a little, and the balance can tip. Fresh water is the enemy of sinking. Rain, river outflow, melting sea ice, and especially the meltwater from large ice sheets all act to dilute the salt at the surface. Fresher water is less dense. If you pour a lot of it into the regions where the conveyor normally pulls surface water down, you make it harder for that water to sink. Slow the sinking and you slow the whole deep return flow. Slow that and you change how much heat the Atlantic can ferry northward. That, in essence, is the leading ocean story people tell about the Younger Dryas. As the last ice age was ending, the great ice sheets covering North America and parts of Europe were shrinking. They did not do this neatly. They pulsed and staggered and sent out surges of meltwater. If, during that delicate time, enough fresh water suddenly poured into the North Atlantic or its gateways, it could have choked the sinking zones. Not with a dramatic, visible plug, but with a subtle shift in density that rippled through the whole system. If you're in Western Europe in that scenario, what you feel is not just colder air. You feel the absence of heat that would otherwise have been imported from the tropics. Winters bite harder, sea ice can expand, Storm tracks adjust to the new temperature gradients between ocean and land. Proxy records give us hints that something like this did happen. In cores of deep Atlantic mud, the shells of tiny planktonic organisms, creatures that lived near the surface and recorded the chemistry of the water in their shells, show changes across the Younger Dryas boundary. Shifts in the ratios of oxygen, isotopes, and certain trace elements suggest that the surface waters in key regions became fresher and cooler. Far below, the species living on or just above the seafloor also change. Some foraminifera that prefer well-ventilated, recently formed deep water become less common. Others, more at home in older, more stagnant conditions, appear in greater numbers. That pattern hints that the formation of new deep water in the North Atlantic may have slowed or shifted its usual location. On the western side of the ocean, off what is now North America, sediment drifts that are shaped and fed by strong deep currents show alterations in their structure and grain size. That too points to a circulation pattern that did not behave during the Younger Dryas the way it did before or after. In the Nordic seas, some records show an increase in sea ice and changes in the assemblages of cold-loving versus warmth-loving plankton species. Taken together, these lines of evidence sketch a picture of a North Atlantic that became more stratified. Fresher, colder water sitting on top of denser layers, less mixing between them, less vigorous overturning. The timing of many of these changes lines up, at least roughly, with the onset of Younger Dryas cooling around the North Atlantic margins. That is why, when people talk about what drove that regional plunge in temperature, a weakened Atlantic overturning circulation sits near the top of the list. But it's important to remember how blurry this picture still is. We do not have a direct gauge lodged in the deep ocean 12,700 years ago that tells us exactly how many cubic kilometers of water were sinking per year. We infer the strength and structure of past currents from indirect clues, the chemistry of shells, the size of grains carried by deep flows, the presence or absence of certain species. Those clues have to be dated, often with radiocarbon, which itself carries uncertainties. Sometimes one core suggests an abrupt change, while another, a few hundred kilometers away, shows a more gradual transition. In some regions, different proxies disagree about exactly when or how strongly the ocean circulation shifted. There is also the question of geography. Did the sinking simply weaken everywhere? Did it stop in one traditional region and move slightly south or east? Did other parts of the global conveyor in the Southern Ocean or the Pacific compensate in ways we don't fully glimpse yet? And then there is the chicken and egg problem. Did changes in winds and sea ice, driven by other factors, start to reshape the circulation, with the fresh water just nudging it along? Or did a big pulse of meltwater force the initial slowdown, with the atmosphere then adjusting to the new ocean state? The data we have can be arranged to support multiple narratives, none of them completely settled. What seems most consistent is this. During the Younger Dryas, the North Atlantic's usual role as a major heat importer into the high northern latitudes was disrupted. Its overturning circulation appears to have weakened or reorganized. In response, the regions that depended most on that imported oceanic warmth, Greenland, the surrounding seas, much of northern Europe, felt a sharper, quicker chill than many other parts of the world. The ocean conveyor kept moving, but it rattled and lurched, and in that lurch, the climates of entire continents shifted. How exactly that conveyor was tripped, by what water, from which route and at what speed, is the next part of the puzzle. When people first tried to answer that what water, from which route, at what speed question, their minds went to a very intuitive place. They imagined a dam breaking, not a concrete dam, but a wall of ice, hundreds of meters tall, holding back a colossal inland sea. At the end of the last ice age, North America did not look the way it does now. Much of Canada and parts of the northern United States were still buried under the Laurentide ice sheet, a slab of ice so thick that it flattened mountains and depressed the crust beneath it. Along its southern and western edges, meltwater pooled in vast basins. One of these, which geologists call Glacial Lake Agassiz, was not a tranquil little lake you could row across in an afternoon. At different times it covered an area larger than all of the modern Great Lakes combined. Its shorelines are still faintly etched into the landscape today, ancient beaches of rounded sand and gravel, high and dry above modern rivers. When you stand on one of those stranded shorelines, you're standing where waves once lapped against a cold, icy coast. Imagine the capacity of such a lake. thousands of cubic kilometers of fresh water sitting right at the margin of the ice sheet. As the ice retreated or shifted, the lake's outlets could change. Sometimes it drained south, down the Mississippi system. Sometimes it drained east, toward what is now the Great Lakes and the St. Lawrence. Sometimes it may have had no stable outlet at all, rising until it overtopped a low divide and carved a new channel in a geologic instant. In the classic version of the Younger Dryas meltwater story, Lake Agassiz is the star. The idea goes like this. As the ice sheet thinned and retreated, the lake's natural southern outlets became blocked or too high. Water rose until it suddenly found a lower pathway to the northeast, under or around the ice, and spilled catastrophically toward Hudson Bay and the Labrador Sea. Instead of trickling through a braided river network, enormous volumes of fresh water poured more or less straight into the North Atlantic's critical sinking zones. In that picture, the Atlantic conveyor is not just gently nudged. It is hit with a bucket of cold, fresh water the size of a small sea. Sinking falters, sea ice expands, and within a few decades Greenland's temperature drops. It's a powerful narrative. It has a clear culprit, a clear route, and a clear trigger. It feels almost cinematic. A hidden floodgate in the ice swings open, and the climate reels. But reality, as usual, is more complicated. When geologists went looking for the fingerprints of such a flood, they did find evidence of large drainage events from glacial lakes. There are over-deepened channels scoured into bedrock, vast sand and gravel deposits called outwash plains, and subtle chemical changes in ocean sediments that suggest pulses of fresher water. What the rocks and mud do not always provide, however, is the kind of precision that story needs. You can see that a giant lake once drained to the northeast. You can date the event roughly, using radiocarbon from organic material trapped in the sediments, or other methods that rely on the decay of isotopes. You can even estimate, within broad bounds, how much water moved and how fast the landscape must have been reshaped. But tying that drainage to a single century, or a single decade, is much harder. Radiocarbon ages carry uncertainties of dozens to hundreds of years. Lakes do not always empty in one clean burst. They can have repeated outflows, partial drawdowns, refills, and more gradual overflows. The geological record often conflates these into smooth sequences. There's another wrinkle. The ice sheet itself was not a static wall. Its margins advanced and retreated. Its thickness changed in different places at different times. Sometimes it was cold, rigid, and grounded firmly on the bedrock. At other moments, parts of its base were warm and slippery, sliding over wet sediments, opening and closing subglacial channels that could route water invisibly beneath the ice. That means that when you ask, could water from Lake Agassiz reach the North Atlantic around 12,700 years ago? You first have to ask, what did the ice look like at that exact time? And that is where competing reconstructions emerge. Some researchers picture a large continuous Laurentide ice sheet still blocking most direct northeastern flow at the Younger Dryas onset. In those reconstructions, major outlets to Hudson Bay are either closed or only partially open. Meltwater from the interior lakes is thought to be heading primarily southward or westward, eventually reaching the Gulf of Mexico or the Arctic via the Mackenzie River. Others argue that by then the ice had already pulled back enough along certain corridors to allow substantial flow toward Hudson Bay or directly to the Labrador Sea. In those models, a reorganization of drainage, helped along by ice-thinning isostatic rebound of the crust, or the unzipping of subglacial channels, could suddenly shunt water into precisely the regions most sensitive to freshening. And then there is the Arctic option. Instead of aiming straight for the traditional North Atlantic sinking zones, some scenarios send fresh water northward into the Arctic Ocean, through river systems like the Mackenzie and outlets from glacial lakes in the western interior. From there, freshened surface waters could have spread through the Canadian Arctic archipelago, down through the Fram Strait between Greenland and Svalbard, and finally into the Nordic seas. In these versions, the conveyor is not punched directly on the nose. It is nudged from the side. The Arctic becomes a staging area where low salinity water accumulates, thickens the surface layer, and gradually leaks into the regions of deep water formation, altering them over decades rather than days. Each of these pathways leaves traces, layers of fine-grained sediments where torrents once roared, a braided bedrock, changes in the types of microfossils in marine cores along plausible routes, shifts in the isotopic composition of foraminifera shells that signal lower salinity. But each line of evidence also has gaps, uncertainties, alternative interpretations. An erosional channel might date to a different meltwater episode slightly before or after the Younger Dryas. A shift in salinity recorded offshore could be the result of changing sea ice patterns or local precipitation, not just a far-travelled flood. A reconstructed ice margin might be off by a few hundred kilometres or a few hundred years, enough to shuffle which outlets were truly open when. As these details are debated, the central tension remains. Big freshwater sources were absolutely present. Giant glacial lakes like Agassiz and its cousins were real, and they did drain, sometimes catastrophically. The Laurentide and other ice sheets were melting, sending seasonal pulses of water along many routes to both the Atlantic and the Arctic. What is still contested is the choreography. Was there a single, dominant flood that tipped the system? Or a series of substantial but not quite apocalyptic outflows that gradually pushed the conveyor past a threshold? Did the critical freshening enter through the Labrador Sea, the Nordic Seas, the Arctic gateways, or some mixture of all three? The records we have are detailed enough to suggest possibilities, but not yet sharp enough to pick one with complete confidence. So the meltwater story stays a little blurry around the edges. You can see the enormous lakes. You can trace their abandoned shorelines, their fossil outlets, their flood-scoured channels. You can measure the subtle freshening in distant ocean cores. The pieces line up well enough to make a freshwater trigger entirely plausible. But the exact route, the exact moment when that water crossed the last divide and began to reshape the ocean, remains one of the quieter mysteries humming beneath the Younger Dryas. Which opens the door for another idea. What if water was not the only player in this sudden chill? The door opens onto space, not the empty, silent kind in your imagination, but the crowded, restless version that actually surrounds our planet. A place filled with dust, gravel, icy fragments, and the occasional larger visitor that crosses Earth's orbit on a long, slow loop around the Sun. When people first started to wonder if the Younger Dryas might have a more dramatic trigger, their thoughts went up instead of out, away from lakes and ice sheets and into that stream of cosmic debris. The idea is simple enough to describe. Somewhere roughly 12,800 years ago, a comet or asteroid fragment enters Earth's atmosphere. Maybe it's a single object. Maybe it's a swarm of pieces from a disintegrating comet. It comes in fast, tens of kilometers per second. Some fragments explode in the air as colossal fireballs. Others might hit ice sheets, or the surface of the ocean, or continental interiors, releasing enormous amounts of energy in seconds. Shockwaves race across the landscape. Fires ignite over huge areas. Soot and dust are lofted high into the atmosphere. The impact or impacts disturb climate rapidly enough to help launch the Younger Dryas. That is the broad picture behind what's often called the Younger Dryas impact hypothesis. To support a story like that, you need more than imagination. You need fingerprints. Advocates of the impact idea went looking, and they argued they found them. In a surprising number of sites scattered across North America, Europe, the Middle East, even as far as South America, researchers reported a very thin layer in the sediments that looked different. A dark streak in lake muds, peats and soil horizons that could be dated within the usual uncertainties to about the onset of the Younger Dryas. Within that narrow band, they claimed to see several unusual signatures. The first were tiny glassy or metallic beads, called microspherules. These are little rounded droplets, often less than a millimetre across, that form when material is melted and then cools quickly while still airborne. They can be produced in volcanic eruptions, industrial processes, or when a meteor hits and vaporizes rock and soil. In this case, the microspherules were reported to have shapes, compositions, and surface textures that looked, to proponents, like high-temperature products of an impact or airburst. Alongside them, another clue, an enrichment in platinum. Platinum is a noble metal, rare in Earth's crust but slightly more common in certain types of meteorites. In ice cores from Greenland, and in some other sediment records, scientists have found small spikes in platinum concentration around the Younger Dryas boundary. That jump, they argued, is exactly what you would expect if extraterrestrial material was suddenly added to the atmosphere and then rained out onto the surface. And woven through those same layers in multiple sites is soot and charcoal, evidence of intense burning. In some places, those blackened particles are unusually abundant right at the time the Younger Dryas begins. To impact supporters, this was a picture coming into focus. a burst of fires on a continental scale sparked by one or more atmospheric explosions or impacts. Microspherules, platinum anomalies, soot-rich layers, all lining up in time. Add in some other claimed markers, like magnetic grains with odd chemistries, or tiny fragments some interpret as melted rock, and the case begins to feel almost forensic. A cosmic crime scene, preserved as a hair-thin line in mud and ice. But if the meltwater story is messy, the impact story is even more so. Those same signals that make the hypothesis exciting also make it difficult to interpret. Start with the microspherules. Under a microscope, small glassy beads are not as rare as you might think. They can be created by lightning strikes that melt sand, by wildfires intense enough to fuse soil, by volcanoes, by human activity in more recent layers. Distinguishing one type from another requires careful work, chemistry, structure, context. Early studies reported a dramatic peak of these impact-style spherules exactly at the Younger Dryas boundary in multiple sites. But when other teams went back to some of those same locations, using similar methods, they sometimes found much lower concentrations or different distributions with depth. In some cores, the peak wasn't exactly at the boundary, or wasn't there at all. Replication, the quiet backbone of science, proved challenging. The platinum spikes too raised questions. Yes, Greenland ice shows a distinct increase in platinum around the Younger Dryas onset. But platinum can move in the environment in more than one way. Some argue that volcanic emissions or changes in atmospheric circulation or even internal ice processes might concentrate it. In some sediment cores on land, platinum peaks appear, but they don't always match perfectly with the proposed impact layer. In others, no anomaly is seen at all. Soot and charcoal tell a similarly ambivalent story. The end of the last ice age was a time of changing vegetation, drying in some regions, warming in others, and human presence with its own fire regimes. Wildfires respond to climate, to fuel availability, to lightning frequency, and to people using controlled burns. A rise in charcoal at a certain time does not automatically mean a skyborne explosion. It might simply track a shift in ecosystems or weather patterns. Even when multiple markers do appear together, there are alternative sources. High-energy wildfires can create their own microspherules as sand or organic-rich soils flash to high temperatures. Volcanoes can inject both dust and trace metals into the atmosphere. Rapid changes in ocean circulation might alter deposition of fine materials in distant regions, mimicking the effect of a distant fallout. There is also the problem of patchiness. If a truly colossal impact or swarm of impacts shook the planet enough to help trigger a global climate shift, you might expect its fingerprints to be unmistakable and nearly universal at that time horizon. Yet the proposed boundary layer is thin, sometimes hard to find, and not consistently present in every well-dated core. Some locations show no unusual microspherules, no platinum spike, no special soot pulse where the Younger Dryas begins. Others show one or two of those features, but not all. This variability could mean a complex pattern of fallout, strongly influenced by winds and regional conditions. Or it could mean that some of the reported associations are coincidental, produced by local processes that just happen to occur near the same time. Critics also point to dating. To argue for a single event, you need many sites to line up not just roughly, but tightly in time. Radiocarbon uncertainties of a few centuries leave room for different episodes to blur together. A fire layer from 12,600 years ago and a platinum enrichment from 12,900 years ago can, within error bars, look like they belong to the same moment when they may not. All of this doesn't make the impact hypothesis impossible. It makes it controversial, on the side of interest, a cluster of unusual signals near a major climatic turning point. Some laboratory results that do seem hard to explain with everyday terrestrial processes. The historical fact that large impacts do happen, even if rarely, and can in principle perturb climate. On the side of skepticism, difficulties replicating key findings, inconsistencies between sites, plausible alternative explanations for many of the markers, the absence, so far, of a clear crater of the right age and scale, and the nagging sense that a climate system already primed by ice sheets and meltwater might not need a cosmic shove to tip. So the impact idea sits in a liminal space, too intriguing to dismiss outright, too tangled and disputed to embrace as the main explanation. When you zoom out, it becomes part of a larger picture rather than a neat answer. a world at the end of an ice age, with fragile ocean currents, retreating ice sheets, large lakes perching on their margins, and perhaps, somewhere in that crowded sky, a few extra stones passing close. What matters for your sleeping mind is not choosing a winner, but feeling the uncertainty. The Younger Dryas may have been triggered by freshwater alone. It may have been nudged by a cosmic event layered on top of that freshwater story. Or the proposed signals may turn out to be a scientific mirage, an artifact of noisy data and our human tendency to see patterns. While that debate continues, another piece of the puzzle waits in the background. Whether or not anything fell from the sky, the Earth itself seems to have burned. Imagine you could stand on a high ridge somewhere in what is now the American Midwest, or the Middle East, or Southern Europe, at the exact moment those black layers begin to form. You don't see a single wall of flame sweeping across a continent. That's a movie image. Reality is messier, patchier, yet no less dramatic in its own way. A storm passes and lightning rakes across a dry hillside. Dead grasses and shrubs catch. A stand of trees that has gone decades without burning finally tips over the edge. Wind gusts turn a modest blaze into a racing front. Hours later, embers from that fire drift downwind into another patch of parched vegetation. Somewhere else, a human lights a deliberate fire to clear underbrush or drive game, and it escapes the intended bounds. Now multiply this, not by dozens, but by thousands of events scattered across a landscape that is changing fast. Retreating ice leaves behind dry, dusty outwash plains. Vegetation is shifting, sometimes accumulating fuel faster than local ecosystems have learned to burn it away. Summers may be getting warmer and drier in certain regions as the big ice sheets shrink and winds rearrange. In that kind of world, whether or not a cosmic spark was involved, the stage is set for more fire. When vegetation burns, it doesn't just disappear. It converts into gases, into ash, into tiny blackened fragments of charcoal that rise in the smoke and drift away. Some of those particles settle close to where the fire burned. Others are carried high, into the upper parts of the atmosphere, where winds can move them hundreds or thousands of kilometers before they fall. Lake bottoms become quiet archives of this activity. Year after year, thin films of silt and organic matter settle, building up laminations like the pages of a book. Mixed into certain layers, researchers find a surge of microscopic charcoal specks, sometimes larger bits as well, evidence that the surrounding region, or even the broader continent, was burning more intensely at that time. In some cores, that charcoal increase coincides with the onset of the Younger Dryas. It doesn't prove how the fire started, but it does say the world, in at least some regions, was markedly smokier. Smoke is more than a smell and a haze. It's made of aerosols, tiny particles and droplets suspended in the air. Some are black, absorbing sunlight and warming the layers of atmosphere they occupy. Others are lighter in colour, scattering light back to space and casting a subtle shadow on the surface below. If enough smoke and dust are injected high enough, they can dim the sun slightly, especially over the regions downwind. Daytime skies grow a little more milky. Sunlight at the ground weakens. Temperatures near the surface can drop, particularly in summer. Volcanoes are the classic example. A truly large eruption can send sulfur-rich aerosols into the stratosphere, where they linger for 1, 2, sometimes 3 years, cooling the planet by a fraction of a degree. Massive fires, like those that followed the Chicxulub impact 66 million years ago, may have done something similar on a larger scale. The key is altitude and persistence. Most wildfire smoke today rises into the lower atmosphere, rains out within days to weeks, and leaves only a short-lived climatic footprint. But under some conditions, especially if aided by intense convection or other disturbances, plumes can reach higher, into regions where rain is scarce and particles can circle the globe for months. Dust behaves in related ways. As ice sheets retreat, they often leave behind broad, unvegetated plains of fine material, ground to flour by glaciers. Strong winds pick up that dust and loft it into the atmosphere. In ice cores and ocean sediments, scientists see changes in dust deposition across the end of the last ice age. Some intervals show heavier dust fluxes, hinting at windier, drier conditions and more exposed sediment. Dust particles scatter sunlight efficiently. A dusty sky is a slightly dimmer sky. Over time, that dimming can cool the surface, especially if the dust is widespread and persistent over large areas. Now imagine a period when multiple things line up. Vegetation patterns are shifting. Summers in some regions are drier, maybe an impact, maybe just lightning and people, trigger unusually extensive fires. Those fires produce more smoke and black carbon than usual. At the same time, freshly deglaciated landscapes supply copious dust to the winds. Charcoal in lake sediments suggests that, at least in some places, this constellation of factors was real. Layers rich in soot appear not only at the proposed Younger Dryas boundary, but around it, in the centuries before and after, indicating a time of elevated burning rather than a single isolated blaze. Other indicators, like changes in the chemistry of ice cores, hint at shifts in atmospheric aerosols and dust load across the transition. Could that smoke and dust have cooled the world enough on their own to sustain more than a millennium of colder conditions? Almost certainly not. Aerosols are ephemeral compared to ice and ocean currents. Even a surprisingly smoky, dusty decade would see its atmospheric legacy fade in a few years once the fires quieted and winds changed. To support a 1,200-year climate state, you need something with memory, altered salinity in the North Atlantic, expanded sea ice reflecting sunlight, deep ocean layers circulating differently. But aerosols don't have to be the whole story to matter. They can act as a trigger or an amplifier. A burst of burning that darkens the sky over key regions for a few summers might be enough to tip already stressed ocean circulation into a new mode. Dust settling on remaining ice can make its surface darker, changing how it absorbs sunlight, modifying melt patterns in complex ways. In that sense, fire and dust are like a match and a gust of wind in a crowded forest. They don't create the trees, or the dryness, or the shape of the valley, but they can decide when and how the flames race through. So when you picture the beginning of the Younger Dryas, you might imagine not just cold and ice, but a preceding spell of murkier skies in some parts of the world. Distant horizons veiled by haze, sunsets reddened by particles high above, lakes quietly collecting a record of falling ash and soot, one dark grain at a time. Above those lakes, the atmosphere clears and clouds move on. Below them, in the deep, the ocean is still adjusting, still storing and releasing heat in slow, ponderous rhythms that pay little attention to a single smoky season. It is in that deeper water, and in the ice that forms upon it, that the longer echo of the Younger Dryas is held. When people think of dimmed skies and sudden chills, they often think of volcanoes. Not the gentle oozing kind, but the explosive ones. The kind that punch a column of ash and gas so high that it pierces through the lower atmosphere and spreads out into the stratosphere, where ordinary weather never quite reaches. Up there, rain is scarce. What goes in can stay for a while. Most of what matters, for climate, isn't the black ash that falls out quickly and buries nearby forests. It's the sulfur. Volcanic eruptions that tap the right kind of magma can release huge amounts of sulfur dioxide gas. In the stratosphere, that gas reacts with water and other compounds, turning into a veil of tiny sulfate droplets. These droplets are bright. Sunlight hits them and is scattered in many directions, some back to space. The surface below receives a little less energy. The planet's albedo, its shininess, ticks upward. The effect is small in any given square meter, but spread over half a hemisphere, or eventually around the globe, it becomes noticeable. Summers come in a bit cooler. Days feel slightly weaker, as if the sun has thrown a thin sheet over itself. We've actually seen this happen in historical time. After the eruption of Mount Tambora in 1815, the following year became known in parts of the Northern Hemisphere as the Year Without a Summer. Frosts in June, failed crops, gloomy, persistent chill. Not an ice age, not even close, but a sharp, memorable departure from the usual. Later in the 20th century, eruptions like El Chichon and Mount Pinatubo injected sulfate into the stratosphere and produced a short-lived global cooling on the order of a few tenths of a degree Celsius. Satellites watched the haze spread. Temperature records watched the response. In all those cases, though, the pattern was clear. A spike of aerosols, a dip in temperature lasting a year or three, and then a gradual return as the particles settled out and rain and time cleaned the air. Now set that against the Younger Dryas. We're not trying to explain a bad growing season or two, but more than 1,000 years of colder conditions, reorganized winds, shifting storm tracks, a climate state with staying power. Could volcanoes have played a role? Possibly, but if they did, it was probably not as a single world-shattering blast that plunged the planet into darkness for a millennium. The physics of sulfate aerosols simply doesn't stretch that far. They fall out too quickly. Where volcanoes become more interesting is when you stop thinking in terms of one eruption and start thinking in terms of many. Imagine a few centuries in which the Earth is a little more volcanically restless. Several large eruptions, each big enough to loft sulfate into the stratosphere, separated not by many decades, but by only a handful of years. One hazy veil thinning just as another begins to form. The climate system, already sensitive for other reasons, ice sheets melting, ocean circulation edging toward some threshold, would feel those repeated nudges. No single eruption would lock in the Younger Dryas, but a cluster of them could deepen the initial cooling, help sea ice expand, reinforce patterns that the ocean and atmosphere were already starting to favour. It's an appealing picture, because it uses a mechanism we understand fairly well, and one we can see in action in the recent past. The difficulty lies, again, in timing. To test the idea, you need to know when, exactly, big eruptions happened around the start of the Younger Dryas. You need to match glass shards and chemical fingerprints in ice cores and sediments to specific volcanoes. You need to line up radiocarbon dates, layer counts, and other clocks with enough precision that you can say, with some confidence, that this particular eruption came just before, or right at, the onset of the cold shift. This turns out to be hard. Ice cores do record volcanic signals clearly. Spikes in sulfate, tiny shards of volcanic glass, sometimes distinct anomalies in acidity. But tying those spikes to individual volcanoes is often guesswork. Eruptions from different parts of the world can produce similar chemical signatures. Layers can be disturbed or missing. Age models can drift by decades or centuries when you look back more than 10,000 years. Some studies have proposed candidate eruptions close in time to the Younger Dryas boundary. A big eruption here, a possible sulfate spike there. Others point out that the dates don't quite line up, or that the inferred magnitudes aren't obviously enough to do more than cause a few cooler summers. So volcanism hovers in the discussion like a familiar character whose exact role in the story is uncertain. Compared to the impact hypothesis, volcanoes are less exotic, more grounded in everyday geophysics. Compared to meltwater and ocean circulation, they are shorter-lived, more of a shove than a new shape. They look less like the architect of the Younger Dryas, and more like a contractor brought in to reinforce a structure that is already going up. Maybe a sequence of eruptions helped tip the Atlantic overturning circulation past its breaking point, or helped sea ice grow thicker and more persistent in just the right places. Maybe they amplified an initial cooling triggered by shifts in freshwater flow or by other forcings we haven't fully identified. Or maybe their contribution was minor, a bit of background noise in a much larger, slower process. The current evidence allows for several of these scenarios without decisively choosing among them. There is no universally accepted smoking volcano whose ash can be traced neatly into the first cold years of the Younger Dryas and whose magnitude is beyond dispute. What we have instead are hints. Sulfate spikes near the transition, scattered tephra layers in ice and mud. Models showing that in principle, a busy volcanic period could make a marginally stable climate more likely to flip. For now, volcanoes sit in that ambiguous category. Plausible helpers, uncertain initiators. Important to consider, impossible to rule out, but not yet crowned as the main cause. And beyond them, behind them, the larger question remains. How does a climate that seems to be easing gently out of an ice age suddenly find itself thrown back toward the cold, and what does that say about the way the whole system can switch from one mode to another? To get closer to that question, you have to step back from individual causes and look at the way the climate system behaves as a whole. Picture, for a moment, a pond on a still day. Throw a small pebble in, you get a few ripples. The surface wobbles, then settles back into calm. Throw in a handful of pebbles, the same thing happens. It's noisy for a bit, then quiet again. Now imagine that same pond on a winter morning, right when it's just about to freeze. The water looks the same, but it isn't. It's hovering near a threshold. A single cold night, a light breeze, a small loss of heat, and suddenly ice begins to form. At first it's a filmy skin along the edges. Then the skin thickens, spreads, locks together. By the next morning the entire pond is a solid, glassy sheet. Same pond, same general conditions. But near that freezing point, small nudges matter in a very different way. Earth's climate, especially during glacial times, often behaves more like that almost freezing pond than like a simple, always stable system. It has thresholds, it has feedbacks, and once certain parts of it start to move, they don't just stop because the initial push has faded. One of the most important feedbacks for the Younger Dryas is sea ice. When the ocean is open and dark, it absorbs most of the sunlight that hits it. When it's covered in bright, fresh ice, a large fraction of that light is bounced back into space. The planet's shininess, its albedo, goes up. Colder air means more sea ice. More sea ice means more reflected sunlight. More reflected sunlight means less energy going into the ocean, which means colder water, which makes it easier for even more ice to survive the summer and spread. From a distance, this can look like a kind of climatic stubbornness. Once the ice grows beyond a certain point, it helps to hold the cold in place. At the same time, the atmosphere above that ice is not passive. When you change where the planet is warm and where it is cold, you change the pressure patterns that guide winds and storms. Jet streams can shift their usual paths. Storm tracks that used to favour one region can move hundreds of miles, bringing more snowfall to places that used to be drier, or cutting off moisture from regions that relied on it. Snow itself is another reflector. Fresh snow on land bounces sunlight away just as sea ice does on water. So if expanded sea ice helps shift storm tracks in a way that lays down more snow over high-latitude land, you've added another layer to the feedback stack. Brighter surfaces on the ocean, brighter surfaces on land, a thinner slice of solar energy actually making it into the ground and water. The important thing here is not that any of these processes are exotic. They're not. You can describe them in a few simple sentences. Cold grows ice. Ice reflects light. Reflection cools things further. What makes them powerful is the way they connect, and the way they behave once you are near a threshold. If the North Atlantic, right before the Younger Dryas, was like that pond about to freeze, sea surface temperatures just cool enough, freshwater layers just stable enough, winds and currents just arranged in a certain configuration, then many different kinds of nudges could have had similar long-term effects. A pulse of meltwater, a cluster of volcanic eruptions, perhaps even a change in solar output or in the background state of the ocean that we don't yet fully resolve in the records. Each one, on its own, might be a small shove, a slight cooling here, a local freshening of surface waters there. But if they arrive when the system is delicately balanced, they don't just produce a brief wobble, they help tip it into a different mode. Once there, the feedbacks take over. Expanded sea ice keeps the ocean beneath it shaded and insulated from direct solar heating. Altered winds keep reinforcing the same patterns year after year. Deep ocean circulation, once slowed or diverted, doesn't spring back instantly. It can take centuries for the great conveyor belts of water to find a new equilibrium. This is one of the reasons the Younger Dryas lasted so long. You don't need a constant, ongoing external force to hold the climate in that cooler state for more than 1,000 years. You need a configuration in which the internal loops, ice, albedo, winds, ocean currents, keep reinforcing one another, like a set of gears that have slipped into a new alignment and now turn together smoothly. In that light, the arguments over the exact trigger, while important, share a deeper common theme. Whether you favour meltwater, an impact, volcanoes, or some mix of them, you're really talking about what gave the initial shove to a system that was ready to move. The sensitivity of that system, its tendency to flip between different stable patterns, is the quiet main character. And while people living through the Younger Dryas had no words for albedo or atmospheric circulation, they were intimately familiar with its consequences. Shifting winds, strange snows, sea ice edging farther south than anyone's grandparents remembered. Seasons that settled into a new, harsher rhythm, and then, confoundingly, stayed that way for many generations. You're born into this new rhythm. For you, there was never a before time, only the stories of it. The way elders talk about winters that used to be shorter, rivers that used to stay open longer, trees that once grew where now there is only scrub and wind. They don't speak about it with nostalgia exactly, more like orientation, a reminder that the world can change and that your people have already lived through one of those changes. Your camp sits in a place that would puzzle a modern mapmaker. To someone looking down from a satellite, it might seem like a poor choice. A valley not quite rich enough to farm, a shoreline that freezes for too much of the year, a plateau where the wind never seems to stop. But your people didn't choose it on a map. They chose it with their feet, over generations. They found the places where snow lingers, but not so deep that it buries the animals' winter trails, where the ice on the river thickens enough to walk on, turning water into a seasonal road, where south-facing slopes catch a little extra sun and patches of ground thaw early, offering the first green shoots when you're most tired of dried meat and old roots. Near the end of the Ice Age, humans are good at this. They have had tens of thousands of years to practice being flexible. In some regions, like what is now Western Europe, bands move in and out of river valleys, following reindeer and wild horses along routes that have been used for generations. The cold pushes the great forests back, opens up treeless plains again, and with them come the herds. Your people respond by ranging farther, by refining stone-tipped projectiles that can be thrown or launched from a distance, by building windbreaks of bone and hide along exposed ridges. In other places, like the Near East, the changes are more subtle. The cold doesn't bring back glaciers there. Instead, it shuffles rainfall, lengthens droughts, makes wild stands of grain ripen less predictably. Some groups respond by moving more often, never lingering long enough to strip a patch bare. Others do the opposite. They build more substantial shelters, dig storage pits, tinker with ways of tending the plants they rely on, so that next year's patch will be a little thicker, a little more reliable. Archaeologists, looking back through the scatter of stone tools and the shadows of old hearths, see hints of this negotiation. Around the time of the Younger Dryas, some sites that had been used lightly for centuries suddenly show heavier occupation. More refuse, more post holes, more signs of people staying put through harder seasons. Not quite villages in the modern sense, but something a little more rooted than before. Elsewhere, the pattern breaks the other way. Caves that were once busy with hearth smoke and paintings fall quiet. Open-air camps appear in places that hadn't seen regular use in earlier, milder centuries. Tool styles shift toward lighter gear that's easier to carry, toward technologies that make sense for people who expect to move often and quickly. It would be tempting to say the climate cooled, therefore people settled here, abandoned there, invented this, gave up that. But human life isn't quite that neat. What the record suggests instead is a conversation between people and their changing world. In North America, for example, the large Ice Age animals, mammoths, giant bison, the great ground sloths, are already under pressure when the cold returns. Overhunting may play a role, so might shifting vegetation, so might disease, or competition with other species. The Younger Dryas adds another layer of stress. Some groups double down on the big game hunting strategies they know, others diversify, putting more effort into smaller animals, fish and plants. Their toolkits reflect this. Spear points become more varied. Some are optimized for piercing thick hides. Others are barbed or notched in ways that suggest fishing, birding or trapping. Grinding stones appear more often, a quiet clue that seeds and tough roots are being processed more intensively. To the people using them, these are not dramatic revolutions. They're small, practical decisions. Add another kind of trap. Learn the timing of a new berry. Move camp 3 weeks earlier than your grandparents did because the animals are moving earlier now too. The cold touches everyday life in 100 small ways. You learn to read the ice on the river not just for its thickness, but for its colour, the faint grey that tells you spring meltwater is running beneath. You remember that one dangerous year when the thaw came fast and the usual crossing swallowed a loaded sled. Since then, your band has chosen a different bend in the river, a different set of landmarks. At night, elders tell stories of winters that surprised them. The year the snow failed and the caribou changed their path. The year the lakes froze so early that fish had to be caught through holes in the ice or not at all. The lesson is always the same. Pay attention. The world does not owe you consistency. Across the planet, different groups are absorbing that same lesson in their own ways. On the edges of retreating ice sheets, people experiment with shelters partly dug into the ground, insulated with turf or bone, catching every scrap of warmth. On coasts newly exposed by falling sea levels, others explore tidal flats, learning when shellfish can be safely harvested in the numbing water. In forests that have crept back into formerly barren lands, still others adapt to stalking deer between trees instead of chasing herds across open steppe. Some of these experiments will fade, some will become the seeds of new ways of living. Later on, when agriculture appears in a few lucky river valleys, and when permanent villages grow from what start as seasonal camps, some researchers will wonder how much of that shift was nudged along by episodes like the Younger Dryas. Did 1,000 years of unreliable seasons make the idea of managing plants more attractive? Did the need for storage, for planning across lean years, give an advantage to groups who were willing to build granaries, share surplus, cooperate more tightly? There are hints, but no simple answers. What is clear is that people were not passive victims of the cold. They were active participants in the story, constantly adjusting, improvising, rereading the clues of wind and water and animal track. You can imagine one family, somewhere on the edge of a glacier or the margin of a drying lake, deciding whether to stay or go. They weigh the memories. The good seasons here, the bad ones. The stories of a cousin's band that moved south and found gentler winters but more competition. The knowledge that if they stay, they know every hollow, every spring, every stand of willow. If they leave, they gamble on uncertainty, on stories carried by other people's voices. In the end, they choose. Not forever, not for all their descendants, just for now. And then morning comes, and there are still hides to be scraped, fish nets to be checked, children to be taught which tracks on the snow mean danger and which mean supper. The climate has flipped into a different mode, but daily life, with its small acts of resilience, goes on. In those small acts, a larger history is unfolding, one that links shifting winds and sea ice to the quiet decisions of families, and that will, much later, shape the pattern of ruins and villages and fields that future archaeologists will study, wondering how it felt to live at the edge of that long, mysterious cold. If you could zoom out from that one family's decision, if you could somehow watch the whole planet through those 1,000 cold years, you might think the pattern would be obvious. The climate flips, the temperature drops, the ice grows, then, much later, it eases back. From far enough away, it feels like a single clean stroke on a graph. Up close, it's anything but clean. Even for scientists today, the Younger Dryas is more like a handful of overlapping stories than a single tidy explanation. Part of the difficulty is time itself. When you look at the Greenland ice cores, the cold seems to arrive almost overnight. Layers of snow and ice stack up like pages in a diary, sometimes with resolution down to individual years. In those records, you can point to a depth and say, here is where the temperature plunged. But move away from the ice sheet and the diary pages get blurrier. In a lake at mid-latitudes, the layers of mud might smear together, one storm erasing the clear line between seasons. In the ocean, sediments build up so slowly that a single centimetre could hold centuries. Radiocarbon dates come with plus or minus ranges measured in human lifetimes. So one core seems to say, it happened in year 1. Another says, somewhere between year 50 and year 200. They might be recording the same change, or they might be catching different ripples of a larger shift. The uncertainty in timing leaves just enough room for disagreement. Then there's the problem of place. The Younger Dryas is named from a little Arctic flower that suddenly dominates pollen grains in Europe. In those records, the cold is sharp and deep. In Greenland, it's dramatic. But in some parts of the southern hemisphere, the signal is muted, delayed, or even out of phase. One proxy whispers that rainfall collapsed. Another suggests it just shifted seasonally. Tree rings in one region show a crisis. In another, they hint at only modest stress. Now imagine trying to write a single global story from scattered, imperfect witnesses. The same pieces of evidence can be arranged into different narratives. If you focus on meltwater and ocean circulation, the freshening of the North Atlantic seems to line up with the cooling. If you're looking at microscopic spherules and unusual peaks of platinum in some sediments, you can sketch an argument for a cosmic impact. If you pay close attention to volcanic sulfate spikes, you can weave a tale where a cluster of eruptions helps push the system over the edge. Each story uses real data. Each emphasizes some clues and downplays others. Climate models sit in the middle of this and try to translate. When researchers feed them big floods of fresh water, some models do, in fact, slow down the Atlantic overturning circulation and produce a colder North Atlantic region with downstream cooling over Europe. That part of the story is encouraging. It says the basic physics of a fragile conveyor makes sense. But those same models often struggle to match the full pattern. They may not cool Greenland enough without overcooling somewhere else. They might miss anomalies seen in tropical rainfall, or fail to reproduce the exact timing of glacier advances in different mountain ranges. When an impact is added to the mix in an experiment, the dust and soot effects are often short-lived compared to what the 1,000-year Younger Dryas requires. The result isn't a verdict. It's a conversation between equations and ice layers and lake mud. In that conversation, some broad points have settled into a kind of quiet consensus. Most researchers agree that the Younger Dryas was real, abrupt, and global in its influence, even if the exact temperature change varied from region to region. They generally agree that changes in North Atlantic circulation played a major role, that large pulses of meltwater were involved somehow, and that humans at the time were responding to a world whose rules had shifted quickly. What remains open is the chain of causes, exactly how much meltwater, exactly where it entered the ocean, whether it acted alone or was nudged by volcanic episodes, solar variations, or even an impact event. Why some regions cooled so sharply, while others changed more gently or even warmed at certain seasons. To some, that uncertainty feels like frustration, like a story that refuses to end. But in science, that tension is productive. Every disagreement about timing sends people back to improved dating methods, to squeeze more precision from radiocarbon curves, to count annual layers with fresh techniques. Every argument over mechanism prompts new cores to be drilled from overlooked lakes, new proxies to be tested that might capture wind or snowfall or sea ice more clearly. Ancient pollen is recounted with better microscopes. Old ocean samples are reanalyzed with more sensitive instruments. Entire model codes are rebuilt to include details of ice sheets, vegetation, and ocean mixing that previous generations had to simplify away. Slowly, the fuzzy picture sharpens. Sometimes it sharpens by proving a beloved hypothesis wrong, and that too is part of why the question isn't settled. The Younger Dryas sits at the edge of what we can currently resolve, both in the archives of the Earth and in the tools we use to read them. Each new method, each deeper core has a chance to shift the balance of the story. In the meantime, the cold snap remains exactly what it must have felt like to the people who lived through it. A real change. Clearly there, obviously important, but with causes that are still, even now, half in shadow. In the Greenland ice, the end of the Younger Dryas looks almost as shocking as its beginning. For more than 1,000 years, the layers record deep cold. Then, over what appears to be just a few decades, temperatures climb back up. Not gradually sliding, but stepping, like someone easing their foot off a brake and pressing the accelerator. To the people on the ground, it wouldn't have been a single dramatic morning when everyone walked outside and said, "Ah, it's over." It would have been a slow accumulation of seasons where the snow seemed to melt a little earlier, the summers stretched a little longer, the storms shifted in character. Glaciers that had crept down valleys would pause, then begin to shrink back. Tree lines that had retreated hundreds of kilometers south would inch northward again. Rivers swollen with seasonal melt would cut fresh channels through newly exposed ground. Whatever had knocked the climate into that strange cold state, it didn't lock the planet there forever. Part of the explanation is written into the system itself. If North Atlantic circulation really was weakened by pulses of fresh meltwater, that fresher water couldn't keep coming at the same rate indefinitely. The ice sheets that fed it were themselves melting, thinning, changing shape. As the big North American ice masses retreated, their lakes drained in different ways. The geography of shorelines and spillways shifted. The huge surges of fresh water that may have disrupted the Atlantic conveyor would have quieted, broken into smaller, more ordinary flows. Saltier, denser water in the North Atlantic could begin to sink more easily again, re-establishing the overturning currents that move heat northward. Sea ice would thin. Storm tracks would rearrange. The atmosphere, sensitive to these ocean changes, would respond with altered winds and jet streams. There are other possibilities perched on top of that story. Some researchers point to subtle shifts in Earth's orbit and tilt, which very slowly change how sunlight is distributed between seasons and latitudes. In that view, the planet was already tipped toward a longer-term natural warming trend, and the Younger Dryas was a cold interruption that eventually yielded to the larger pattern. Others note that greenhouse gases like carbon dioxide and methane were creeping up again by the end of the cold phase. Part of that rise may have been feedback, warming oceans releasing more CO2, thawing wetlands breathing out more methane. Once those feedbacks gathered strength, they could help pull the climate out of its deep chill, and just as with the onset there's room at the margins for volcanic episodes, for small changes in solar energy, for complex interactions among ice sheets, vegetation, and clouds that models are still learning to capture. No single tidy mechanism has won the argument. The broad families of explanations all share a theme, though. They treat the Earth not as a machine that switches cleanly between two gears, but as a network of balances: ice changing sea level changing ocean circulation changing where heat and moisture end up, vegetation, dust, greenhouse gases, and even the colour of the planet's surface feeding back into that loop. Interrupt one part of the system strongly enough, and you can tip it into a colder, drier arrangement for centuries. Let that interruption fade, and the same physics that made the cold possible can guide it back toward warmth, though not necessarily to the exact same climate it left. For modern eyes, used to imagining climate as a smooth, gentle curve, the Younger Dryas and its abrupt ending are a reminder that the planet can surprise us, not just with sudden downturns, but also with surprisingly rapid recoveries once the underlying forces change. They don't offer an easy comfort. The past doesn't promise that every disruption will be brief, or that every system will bounce back on human timescales. What it offers instead is a sense of depth. It tells us that our climate has hidden thresholds and feedbacks, that big ice sheets and oceans can reshape wind and rain in ways that feel disproportionate to the initial push. It also tells us something quieter. Even when the cause of a shift isn't fully settled, the traces of that shift can still be read with care. In trapped bubbles of ancient air, in the chemistry of shells, in the muddy bottoms of forgotten lakes, the Younger Dryas warms back toward the kind of climate in which agriculture will eventually flourish, in which cities will be built, in which we now lie awake and wonder about a cold that ended 11,700 years ago. We don't yet have its full story, but the fragments we do have are already enough to show that our planet carries its own memory, written in ice and sediment, waiting for patient minds to listen. As the graphs level out, as the glaciers shrink back into the high mountains, the world that will feel familiar to us begins to take shape, and somewhere between that last hard winter of the Younger Dryas and the first generations who never knew such deep cold, the long night closes, leaving questions behind it that we are still, gently, trying to answer. So now, lying here at the comfortable end of that ancient story, you can look back over the long cold night with a little more clarity. We don't know exactly what triggered it. We may never fully untangle how much came from meltwater, how much from impacts or volcanoes or slow orbital shifts. Those arguments will probably continue for decades, shifting as new cores are drilled, new models are run, new fragments of evidence come to light. But some pieces feel solid underfoot. There really was a sharp return to cold about 12,900 years ago. It really did last more than 1,000 years. It really did leave fingerprints scattered across the planet, in Greenland ice, in European pollen, in North American lake beds, in dust blown across distant oceans, and it really did end, quickly, just before the world in which all of recorded history unfolds. The open questions still matter, not just for curiosity's sake, but because they tell us how sensitive our climate is to being nudged, how easily patterns we take for granted can bend or break. If this journey has kept you company tonight, you can help it find its way to someone else. When you're ready, you're welcome to like this video, subscribe to the channel, and leave a quiet comment. Tell us where you're listening from and what time it is there, as the last traces of that ancient cold fade into your own present night sky.